Okay, now I think this is recording. Of course, I will not recap everything for the recording, um, but it's important that this is recorded. So thank you. Right. So as I was saying, so the electric sector contains four generators. Three of them are the generators of the SU2 algebra associated to the SU2 group, and the U1, this U1 symmetry, the U1 hypercharge. And there are four generators that you see they break in the vacuum. There is only one combination that preserves the vacuum. At the same time, is the generator of a new symmetry, which is the electromagnetic symmetry. And this is this generator, which is tau 3 plus y. I said that there are some authors that they write Q as tau 3 or T3 times plus y over 2. You will see this often as well. So this is exactly the same thing, but the difference is that I had to take care of this because if I was using the y over 2 in this table, well, in this one, for example, I would have to divide all the E1 charges by, in this case, multiply all of them by a factor of 1. Sorry, by a factor of 2. Of course, not 1. By a factor of 2 here in this, for these hypercharges. And of course, for the same for the electrons. So some authors or some references prefer the y over 2 definition, and then they have the hypercharges accordingly defined. Some other ones prefer only the y. I don't have particular preference. Just use the y because this was the way I also use. I wrote the charge, so I have to be consistent. So this is also possible. This is also possible. But you need to multiply. Charges by 2. Okay. Good. So let's then move on. I will just step this slide. It was on the side note. Right. So let's now look into the unitary gauge in the case of the standard model. So you have already seen the unitary gauge. Well, Jean seen previously.
Well, I have a question.
Yes.
Why is the boson always written as a doublet?
Because it's a doublet. it's charged under SU2 cross U1. So it's the quantum numbers. It's as I wrote before, as I can write here. So the Higgs, so phi. Let me see where the phi is placed here. Phi. And now I use this symbol just to say this is how it transforms. What are the transformation properties? So phi transforms as, let's put it this way, as a singlet of SU3. It doesn't have color, right? But it transforms as a doublet of SU2, and it has hypercharge, which is 1/2. So this is how these are the transformation properties, and this needs to be a doublet. Otherwise, you would not be able to generate masses in the standard model. You will not couple it in the way it should be coupled.
Because we were in the excess, we were always using the Higgs as a
yes. In the other essays, but that was like the first course, the first module, the SM1 model, was an abelian model. This is the realistic model now. But the thing is, it's a lot better to introduce the concepts, or a lot easier to introduce the concepts in an abelian case, and then generalize to this. Because this, as you will see today, it adds up a lot more things that you don't have in the abelian case, in the U1 cross U1 case. That's why I call the abelian standard model, because the main key features are there, but it does not have like the entirety of the features that you see in nature. And the standard model itself, the non-abelian, standard model does indeed contain these features observed in nature, and that we will discuss some of them today. So, was it clear now?
Yes.
So this is really a phenomenological need of the Higgs boson being a doublet. Not the Higgs boson, this is the Higgs doublet. The boson, let's make it also clear. The Higgs boson is going to be this H.
Yes.
This is the phi is the Higgs doublet. And when we say Higgs doublet, we are talking about in a pre-electric breaking, so an electric preserving vacuum. That's a Higgs doublet. Then you break the symmetry, you remove the degrees of freedom that are no longer necessary, or they are absorbed, they are bosons, and you are left only one real, this is a real scalar. You are
So
left,
then we break the electric symmetry.
yes,
So
yes.
in our current universe,
We have electric broken symmetry. Our current universe only has two symmetries. Our current universe has SU3 color, preserved, times U1 electromagnetic, not U1Y. This is our universe. Our universe. But of course, forgetting about gravity here, there is also gravity, but forgetting about our quantum universe, our confirmed quantum universe, say, or the quantum side of our universe it is. And in fact, this has remarkable consequences. And the fact that the electric symmetry existed as an exact symmetry before, you can see as the electric symmetry as like a no longer exact symmetry. It's no longer there, it's broken, but features of the electric symmetry are present, like the existence of W bosons, the existence of Z bosons, and also some interactions, weak interactions itself, that correspond to a broken symmetry, but they are there, these weak interactions. And they are responsible, for example, for the sun to shine. Right. So what are what is the Higgs boson the Higgs doublet looking like in the unitary gauge? So first of all, you can put the three goldstones as a phase. Previously, you did with only one goldstone as a phase, which was a simple thing to understand. Now you put the three of them here, and you have these TA generators here. Yes. You have these TA generators. What are these TA? So we have seen, so these are the T's that preserve the electric symmetry. So you have T1, sorry, the ones that break, not preserve, that break, because these are ones associated to the goldstones, and the goldstones are attached to the broken generators. So we have the T1, the tau2, and we also have, so T3 is going to be this tau3 minus y. This is orthogonal to the tau3 plus y. If you write in a matrix form and you make the product of those two, you see it's zero. So this is like an orthogonal combination of the tau3 plus y generator. And you put these three generators here in this exponential. Now you look at the gauge transformation. So it's following the same path, the same steps that we did before. Now you compare the gauge transformations of the field phi. Initially, so you have this tau A and omega A. Omegas are just the parameters of the transformation. So these are space time dependent because this is a local symmetry. So we are talking only about gauge symmetries at the moment. So these are local symmetries. And this omega 4 is the one, what we called before as alpha, for in the case of the one symmetry, alpha x. And similarly, this is just to recall, to remind how the transformation of the gauge fields come. And now we can use our gauge freedom to choose what is the gauge that will allow us to remove this exponential. So this is an easy exercise. We just put another exponential here with the same argument but opposite sign. But you say that other opposite exponential is this one here. And then you equate things. Um, exactly, and you define the field as 5 prime. Now you equate things and you realize that this is what I was saying. So you put this term here. This is uh, the gauge freedom that we have. And now you equate things and you arrive to this conclusion that you can identify your omegas in terms of your Golsons in this way. Jean, if you want to see this more, because this was not in last year when you read the notes, this was not properly written there.
Could you just
Not
scroll
a little bit up, yes.
Okay.
Was here. Lecture 7 of the first module has a long explanation for this in terms of Q1. So if you want to understand better what happens with one, because here I am not going to repeat all steps.
And I was just thinking that since it's not clear to me that you can sum the arguments of the explanation because the generators don't do not commute, but I don't even think that's the point I'm trying to make.
This let me think. But here what you are doing is, so this is one of your this is the transformation of the fields give this, because you have this. So this is the definition of the transformation. This is
because you are working the infinitesimal.
exactly. Well, here it's written sort of in an exact way, but yes, the infinitesimal, it's like the deltas, the delta precise, and then you got delta precise plus something which is this argument at leading order, of course. So you have that, and then you have the freedom to choose to say, okay, I want the Goldstones also in the exponential, but I want to get rid of them. And I have the freedom to do that, but that will fix what are the omegas. Instead of omega, now we will no longer say, now omegas, or alphas in the case of Q1 as we call, they are no longer free parameters that can be whatever. No, they are no longer whatever, they are something. And that something is a particular choice to remove Goldstones from the theory. And when we say from the theory, it's not only from the scalar potential, but also from interactions with fermions, of course, and also from the kinetic terms. It also removes the Goldstones from so that's why they become non-physical, because they no longer have kinetic terms. If they were still having kinetic terms, they would be physical massless particles. And this is what is explained in the lecture 7, João, that I recommend you to have a look, either to the notes or directly to the video that is on mine. And because there I have shown what happens to the kinetic terms and what happens when you expand the potential and the yeah, exactly, the covariant derivative applied on phi, and then you see there is a possibility of transforming a Goldstone into a gauge boson, and that's I call that an offending term because that was not in a mass diagonal basis, and we could not interpret our physics based on that transformation. At any point, a boson could become a gauge boson, so that's not a physical basis where you need to be diagonal. You need to get the eigenvalues of a diagonal matrix, which is the mass matrix in this case, and that was not the case. I have shown that with this prescription, you can remove that even from the kinetic terms. But
we don't consider those bosons because we can see them in nature, so they disappear from our math.
yeah, well, we don't see Goldstone bosons in nature. We have not seen Goldstone bosons in nature. There are severe constraints.
Always particle physics or in other areas like condensed matter physics, we can.
In condensed matter physics, it's a good question because you have broken symmetries there as well, spontaneously broken symmetries. Now it's just the question is, and this I don't know the answer, is whether those symmetries are local sort of gauge symmetries. They have this sort of phonons, this kind of thing, which is kind of.
But with the same thing, and I think we covered that in the condensed matter. You do basically the same Hessian matrix.
Yes, yes.
But then you can have like negative masses and whatnot.
You can have negative masses in condensed matter.
Effective masses.
But negative?
Yeah.
Okay, but that's before you have a phase transition.
No. I mean, yeah.
But that happens before the phase transition, right? So before the phase transition, you can have negative masses. But after the phase transition, because negative masses indicate that you are not in a
negative
stable.
mass. So I think there's actually like an electron in the field. It will essentially mean that it goes the it can be a hole, right? So it's something. It essentially means it goes the other way.
But that's
You apply force and it
Yes.
goes the other way. So it's effectively a negative mass.
okay. It's more like a repulsive force.
But yes, magnons, for example, are.
Yeah, that's.
Symmetries, polarons, all those kinds of.
I really don't remember the details, but that I think that is in a great analogy with this sort of things. So on that ground, if those are, if these magnons and these phonons, if they show up, I don't know, but in principle you don't have goldstones there. They are absorbed well.
I think
Because those are kind of a mass, right?
But I think there are, because there are two kinds of bosons, phonons that are optical or acoustic.
Yeah.
And when one is massless because it's a linear.
Ah, okay. So that's in principle goldstone.
So Goldstone bosons can be seen in it.
If you are talking about the Goldstone bosons in terms of purely in the terms of symmetry, and this example that John gave, and the disclaimers that I don't know condensed matter physics enough to, or I don't even recall some of the details 15 years ago or 10 years ago or so, to be aware at this time if those are equivalent to the Goldstone bosons. But that the description that you just gave and you have this pressure in your mind seems like. And but that's not a fundamental Goldstone. That's an effective description. Like pions, you heard about pions, right? Pions, they would be goldstones of something called a chiral, like not this chiral symmetry. Well, it's related to this one, but this chiral symmetry breaking, the effect of chiral symmetry breaking is what allows pions to acquire a mass. And so that's why they are pseudo goldstones. But they are composites. They are not fundamental. They are made of quarks. So there is like all this confinement. There's this confinement theory of QCD itself.
But still, a Goldstone boson makes sense because there's mass term that you can remove.
Yes, exactly.
They are not.
That you cannot. Yeah. If you have a mass term, you can no longer remove it.
They're not Goldstone bosons.
Because when you have a mass term, and let's say we are also talking about a global symmetry in that sense. And if it's a global symmetry, you don't have the freedom to gauge it away completely, because what happens here is that you do this thing to the scalars, but you also need to modify the A's and B's, and they get here, they come here, and this is why you can really remove them once and for all, as you remember. Because if you don't have gauge bosons, you remove them from the scalar potential, but they appear back in the kinetic terms, and with interactions. Then you expand the kinetic terms, and you have interactions. One of the exercises of the first example, I mean the third exercise. The third sheet, one of the exercises was to compare this. So, but here the procedure is exactly the same. You identify your gauge, so that this omegas with the G's, G's over V, and V of course this is to keep the dimensions, and it comes from this definition that we put V here. Of course, also recalling that to first order, when you expand this, you recover the canonical form of the fields, like phi1 plus I phi2, phi3 plus I phi4, so it gets a form, but it's not the same. The bosons don't have exactly the same. They don't appear exactly in the same way. But the structure is there. And also there are this is just to say there are some authors that use in this T8 in this exponent tau A. So the rigorous way is doing like this because you are using the broken generators. But you can also do like this. Some authors do like this because they argue that this identification of bosons at the end of the day, this is a SU2 rotation. So you have the freedom to rotate your field in such a way that, or it's an alternative, it's another choice. I understand this better, but this is also another rotation that will fix in a slightly different way your omegas, your parameters, but also works because at the end of the day, we are talking about rotations in the SU2 space to do this. So, and this is what, once again, what was shown in the first like lecture 7, that we have shown that identifying. So now we are going to work with a prime, with prime fields. So we are going to work here, but I will remove the primes from here onwards so that to make the notation not as heavy. But the point here is that because of gauge invariance, we are only doing a gauge transformation here. And this is only a gauge transformation, what we are doing. So we are defining the field, and now we apply the gauge transformation here. And we know that the Lagrangian is invariant under this transformation. It's the same here. So we apply this gauge transformation. So we know this. And it's from knowing this that you can show that the Goldstones are removed. And with that in mind, you say, okay, because this is a theory of gauge invariance, I will start looking from here till the end of my days. I will only look at the Higgs doublet written in this way, about the vacuum, with this expansion H about the vacuum, these quantum fluctuations. And the scalar potential becomes as simple as it is. There is only one real. So from one doublet, one complex doublet, you end up with one real Higgs boson, and this is the standard model Higgs boson. You find quartic interactions, cubic interactions, a mass term, and look, this mass term has exactly the same values obtained above when we did diagonalization. So this here was only substituting, this was obtained only by substituting this. And we got that, because we are already saying this is the minimum. And if that is the minimum, we find the mass. This is already diagonal. And above, just to refresh your minds, let's go above again. Here, you see? So this was the mass that you got. And all the other things that were massless, they don't show up there. They are the bosons, the ones that are absorbed into and they are eaten by gauge bosons. This is how we typically say it. If you count the degrees of freedom, I've done that in the other lecture. Here it's the same. You have in the beginning, so either the gauge bosons were massless, and being massless, they only have two polarizations, two transit polarizations. And you have 4 degrees of freedom in scalars. What's happening now is that you're removing 3 degrees of freedom from scalars, but adding up 3 longitudinal polarizations for the double plus, double minus, and Z boson. So the scalar degrees of freedom, because at the end of the day, these are scalar degrees of freedom, they match before and after the breaking, and that's the important part. You don't invent and you don't remove degrees of freedom in this process. Right, of course, here you know you can draw these interactions with the Feynman diagrams, but let's step that for now. Okay. Now let's expand the covariant derivative, because now what we want to look is to the Goldstone, to the gauge boson masses. To look into gauge boson masses, we want to couple the Higgs to the gauge bosons. and evaluate it next to the vacuum. So making a shift around the vacuum and see which masses do we obtain. This is the essence of the standard model. This part. This was the way. So one of the when the W's and sub-bosons were first postulated and then observed, it was said, okay, we have the gauge principle, but the gauge principle seems to be not respected because we have massive gauge bosons, and everyone were used to electromagnetic theory where the only gauge boson known to date, the photon, was massless, well in agreement with the gauge principle. But here there is a way with the introduction of the Higgs mechanism, and in fact this is the Weinberg-Salem model, Weinberg, Glashow, and Salem. This is a way of consistently and in a gauge invariant way giving masses to gauge bosons. So
before the symmetry breaking, could we say that those bosons were massless?
exactly, you can
So all
you
particles were massless
yes.
before they.
If you go up in energy, if you go to the very beginning of the universe, or if you zoom in a lot into the nucleus, gauge bosons become massless.
So that's why they say Higgs gave mass to present.
Yes, Fermi as well.
Well,
We'll see that
then Higgs
today as
comes
well.
to Fermi.
Yeah.
It does. To everything in the standard model, including the Higgs itself. Everything with mass. Everything is mass. But the mass of the Higgs boson is like we postulate a scale there. We put a new term in the potential, this mu phi dagger phi. That's postulating a scale. That's not the Higgs boson mass, but that will give you the scale. Because you have, this is the mass, right? This is the mass of the Higgs. But you have this minimization condition that was given above. There you go. We have also seen this. You have this minimization condition. And this is the guarantee that you are giving. So you replace mu by minus lambda v squared. So you see, mu and v are associated. You take this from the first derivative. Recall that. From this, you take the first derivative. You get this expression that which is equal to 0.
How do we measure the vacuum expectation value? I understand that you can measure the mass, but
you measure it through the measurement of physical masses.
okay, you know the coupling.
Exactly.
Okay.
For example, you know the gauge couplings very well, and you with that you measure the gauge boson masses, and you can extract. That's one possibility. But you have crossed information from various sources where you can get this information about this. If that verb is like only one, or if that's a combination of various verbs, it's a different story. We can talk about this Thursday, possibly. Let's see. So the covariant derivative, it's in general a matrix. So this is, I'm stealing this from what we have discussed in the previous lecture, when we mentioned about Yang-Mills theories. Here, I'm writing this in terms of the symmetry of the standard model. Of course, there is a U1 part here, which is not the Yang-Mills. The Yang-Mills part is this here. But this is also, there should be here a delta, actually, to make this consistent. Right, so I should put here, and I should put here a delta. I'm putting the generator after the matrix. So the generator Y is already a matrix on its own, but let's write delta A B just to make it concrete. And Y, the value of I will be equal to the hypercharge of what is the covariant derivative applying to. So you have this phi, in this case, it's 1/2. So we can expand for the Higgs, this is the Higgs doublet. Let's take y equal to 1 over 2, and let's expand this covariant derivative and see this in the matrix form. So you have this structure here, and now these ones that I identified here in red. So you see that this corresponds to generator 1 and 2. So you have the A mu 1 and A mu 2 fields here, and A3 fields and the B mu fields you have in the diagonal parts, of course, because this is proportional to identity here. So B's are proportional to identity, it's diagonal. Also, A3 is proportional to T3. And T3 is like the third isospin generator. So it's 1 minus 1. You know that very well. So that's why you have a plus 1 here. So in fact, minus 1 here because this is defined with a minus. So you have plus here. And you have minus here, because the minus of here is being absorbed into the plus. Just the definition of the covariant derivative is a minus here, so it reverses the signs here and here. Right, now let's observe the following. Let's recall what were the isospin ladder operators that we can call T plus or minus, which is simply like 1 over 2 sigma 1 plus or minus I sigma 2. And writing this in this way, we can recast the off-diagonal parts of these ones that are in red here in the following way. So take, for example, exactly, these are the two of them. You pick up these terms and you expand in terms of this T plus and T minus, and you identify these two possibilities. And now you see one of them is for this component, and the T plus is going to be with respect to that component up there. And you can call a different name to this A1 and A2, a more familiar name, W plus, T plus, and W minus, T minus. Where this is the definition, we have defined this the combination of A1 and A2 in this way, with this, so A plus or minus is equal to A minus plus A1 minus plus I A2, and this 1 over square root 2 is a normalization factor. So this is a vector 1, 1. It was a vector which is 1 minus I, another one is 1 I, and these are not normalized, so this is easy to normalize. You have this 1 over square root 2 factor. The things should always be normalized, otherwise you will get weird results with the calculations. So you can recast the covariant derivative in this form. This is just identifying things, and you can. This is how you can recast. Now, and recalling again. So this is small, but it's to recall again that we are using this doublet to substitute here. I didn't have space to write here, so it's written here in small. You from there don't see it very well. Perhaps you could like turn that a little bit more towards the center, or is it possible? Or
Let me see. I don't think you can tell it, but maybe you can reduce the size of the image.
Yeah.
So the size of the image is its menu, right? No, there is zoom here also.
Oh, that's should be different. That's actually zooming in. That's different.
Yeah.
But what if you do the other one?
No.
No, it's not.
Crossing the image.
This is. It does not go less.
Yeah.
Yes. It would be good to go that way.
I think we would have to go off there.
Okay. Well, if you can read, it's okay. Just
What if you try the last information?
sorry.
Yeah, maybe. Don't. Yeah.
Let's keep it then.
This works.
Well, yes.
Ah, yes, great. Very good on those. Let's keep it as it is. Now you just have to.
It's not kind of like.
Yeah, but then it will start going out of the board.
Great, this is pretty much better now. Thank you. Okay, so where were we? Yeah, so we are talking about this covariance derivative. Now we apply to the Higgs doublet, and we obtain this. So this is after acting the covariance derivative, like here, and of course the same for the conjugated part, where instead of W plus you get the W minus, and here you get the plus one, this one, and you'll get the minus one. So I couldn't refer to here. So this is what you get, and now to go to the gauge boson masses, what you do is to compute this Lagrangian term. These are the kinetic terms of the doublet. So the Higgs kinetic term, let's say.
Anyway, that symbol next to Lagrangian, I see it in some art. Does that
This
mean
one.
that thing is a term of
Yes.
the Lagrangian?
It means that there are more things. So the electron with Lagrangian doesn't have only this.
Yes, of course.
There are more things.
Contains
It contains, yes. So, yeah, exactly. It's updated. So here it's like the Lagrangian is bigger, pretty much. It has more things than what is shown here. Yeah, this is very often seen, even in papers. It's a way of being lazy exactly in an elegant way, elegantly lazy.
That's what I thought. So that makes sense.
Right. So you expand this, and you get this term. So I'm identifying the most important with the three colors again. Now it's less elegantly lazy, but it's not important for the discussion for the time being. It will be later. But you get a term for the W's, and this is already a mass for the W bosons. These are the charged one, and you get this term here, which has a diagonal mass terms for A3, diagonal mass terms for these, but there is off diagonal terms here. So we need to do something about it. This is not yet a physical. This is already without the Goldstones, but it's not yet a physical. Yes, about
Just looking at the master, I mean, it's two kind of different fields, but should we think that because they're charged, should we think of it in the same way that we think of the Fermion master, which has
Yes.
pi bar and phi?
talking about this, right?
Yeah.
Exactly. So since they are charged, and in fact, the charge eigenvalues are given by the ladder operators. Let's say if it's one is the plus, the other one is the minus. And the ladder operators, in fact, what they do is they transform double plus into minus and vice versa. You can think that as spin minus one plus one, something like that.
Yeah.
Let me go. Oops, I'm going too far. But yes, the thing in terms of symmetries here, first of all, you need to build an invariant. You do not build a W minus plus W plus. That would be badly breaking the electroweak symmetry explicitly. So we don't want to do explicit breaking of gauge symmetries. That's like a golden rule. If you are extremely lazy, and if you have the ability of writing in a very convincing way, maybe you can find the arguments. But that is not, it's like you are using the gauge principle and at the same time ruining it. So this is, that's why I say it's a golden rule, and you cannot, if you want to do it consistently, you should preserve the symmetries that are there. And in fact,
But sometimes we introduce soft symmetry.
we do, but the soft symmetry breaking is for global symmetries. And there is a way of regarding global symmetries. Global symmetries, they exist in nature, but are not exact. So this is the rule of thumb. Gauge symmetries are exact symmetries, the preserved ones, of course. But even in a more primordial phase, gauge symmetries are exact symmetries. Global symmetries are they may exist, they may do things, but they are not exact. And not being exact, it means that they can be violated by small effects, tiny effects. And this is also a contact point with gravity in a way, because it is often seen that we have never seen a global, continuous global symmetry, a global V1, a global XC2, exact. First of all, we've never seen fundamental bosons that would resemble, and we have restrictions even of the possibility of the hypothetical existence of the global bosons. They are really strict restrictions. But we have never seen any trace of those global bosons, which means that, okay, there are no global symmetries that are spontaneously broken. This is the first interpretation of that. The other is, if those symmetries exist, they are violated by some effects, and one of those can even be quantum gravitational effects can violate them.
Maybe I'm not too far, but it wasn't a completely global symmetry violate causality. The field would change everywhere.
I don't see that immediately. Why would it violate causality?
Because it's not a function of
If you want,
it's internal degree of symmetry. So
it's internal degrees of freedom. It's not. I'm not talking about.
but if you change the field itself,
It's just a
would change.
coordinate transformation in the field space.
Yes.
There's nothing
Yeah,
physical.
we have the example now, rotate the entire space time at the same time.
Yeah.
Yeah, exactly. No, but that's not space-time. But even space-time symmetries can be localized. We can make the like the Poincare symmetry a local symmetry.
And it's only a local symmetry because
I mean, but gauging it in the sense that okay, it's a symmetry of space-time transformations,
it's not only local because in your gravitational field.
but it's not local in the sense of
It's global because it's you that start to move with respect to the reference frame. So that's why you see everything
Okay.
translated.
exactly.
It's not like you're translating the entire space and it's you that's going through the space.
Yes, that's the point. But you can make it. You can be ambitious. You can make a local symmetry together. But for that, you need something else. You need supersymmetry for that to complete the algebra with anti-commutating operators. This is called a graded algebra, and that gives rise to supergravity when you do that. But that's I don't even like a lot of supergravity, but it's the principle is interesting, of course. Now going back to the standard model. Yes, Oswald. So this is an invariant operator, and this comes out directly of this expansion. And now we have this one that is not diagonal. So these A's and B's are not yet our gauge bosons. So the very immediate way to convince ourselves about this is just diagonalizing this mass matrix. So you're writing in the basis AB, and in this basis AB, so this G square is the A square term. Then you have the G prime squared, which is here. It's the BB term, and then you have the AB and BA, which is with I should put a minus here. If this minus is correct, there I should put a minus here. And then you have this minus B minus GG prime minus GG prime. I need to revise this. I don't recall to have this minus here, but I know it should work. I will revise this later on. What happens is that then you get this, you diagonalize this mass matrix, and sorry.
It's right. That's basically that is those
Yes.
values.
Yes, yeah, exactly, because it's in the off-diagonal part, and it one cancels with the other one. Exactly. Yes, it does. So you get the eigenvalues, and you have one massless and a massive one. So this is a pretty much trivial process to do. Even by hand, you can arrive to this. So you can already come to a conclusion that you have a massless field, which is a photon. You have a massive one, which has this mass, which is the Z boson, because this is the one that couples to the photon. I mean, the one that couples to the photon should, in bilinear terms. So since the photon is neutral, the Z boson, the other should also be noticed. So this is the Z boson here, and also from this other term here we have the double bosons. So we have already seen how to give masses to the Higgs boson, to the double bosons, to the Z bosons, and how to obtain a massless photon in theory. This is the essence of the standard model. It's explaining this feature here. And this is only possible with phi being a doublet because of the SE2 algebra, and without, if it's not a doublet, we cannot couple it in this way. You could couple it to the U1 part, to the D part, so you could do something to B, but not to the other, to the SE2 part. But doing it to the SE2 part, you get exactly the same things that you see phenomenological. So, Marco, this is going back to your original question. This is why the Higgs is a doublet. The standard model Higgs is a doublet. You can have others that may be singlets, triplets, quadruplets, and so on. That's going to be one. I want to talk about that maybe next lecture as a bridge to new physics. Now, one of the things is that here, these are written in terms of couplings that are not exactly the ones that we measure. We are in an electromagnetic theory, in fact, so we can measure the electric charge, what we call E, so we will call this E parameter. We can measure mixing angles. And that's why I'm introducing here the Weinberg angle. And the Weinberg angle is the angle that rotates from the gauge basis to the Mice basis. And this is a well-measured angle through this sine. So sine square equals to approximately 0.53. And is defined in this way. So you have the gauge basis, and you rotate it to the mass basis in this way. Of course, you could put the minus in different places. It would change the notation. So as long as it's an orthogonal matrix, it's fine. It works whenever you put the minus sign. This is the convention used in the standard model. But in the exercise that we took at home, this was not always a convention. Also because it's not unique. So we have already seen this.
We exchange the cosines and the sines. So we get the real relation matrix. We'll get the same thing.
Yeah, it's determinant is -1.
What's the problem here?
Determinant is -1,
But
No, this is an orthogonal matrix. Yes.
You rotate and then you invert it.
yeah, that's the rotation.
well, in the exercise, in the exam, the minus is on the other side.
Yes, it is. It's a phase. Putting a minus in a different place is also a phase, which is not physical. A phase that can be absorbed, so it's not problematic at all. In the fermions, those phases play a role. They are CP phases, but here in this case, it's not problematic. I mean, since it's a orthogonal matrix, we are not talking about phases. But if you put the minus in the cosine, this will change the definition of the angle. That's what would happen. And this is to be consistent with this measurement, the sine square. Otherwise, you would have to call it the cosine square.
Because they call like an angle, but there isn't a real analogy with the rotation.
No, there is a rotation.
There's no rotation and inversion.
There is a rotation in the same way that when you do this, like you have some x is equal to a rotation matrix and x prime. This is exactly what you have here. So this is not an analogy. This is exactly a rotation, but a rotation in the internal space. You see, it's not a space time rotation. It's not a rotation that you rotate.
But if you recall the rotation matrix, and the cosines and the sines switch other places, the determinant used to be 1, and this is the case. In fact, the determinant here is
It's -1.
Yeah.
it's fine, it's -1.
You're saying that it's counterclockwise direction.
But
I think it's not.
it was just one small.
This is the regular rotation matrix with the sigma x.
Inversion, yes, but that's what it means. If you rotate it, then you invert it.
Yeah.
You rotate the other way around.
No, because you have the Well, it depends on whether you care about direction.
It's kind of hard to see what an inversion is.
Well, it's here. It's that's not a physical problem. That's the bottom line. It doesn't matter physically, really. Then you measure these quantities and it's a sine, the sine square. But this can really be seen in a rotation. And yeah, the sign of rotation has to do with the way you are doing it. And here you can redefine the angle in a different way. If you define this as theta goes to theta minus pi over 2, then you and then you get the new theta prime and you get plus in sines. So theta, yeah, and then you get cosines and sines. So yeah,
And then you get everything okay, just
exactly. So this is like the rotation of pi over 2.
you just need some pi over 2 and you get
Exactly. If you want to be, the thing is, this is what is used to be consistent. But if you change the angle by a certain amount, you go to any rotation matrix that you want. Change it by pi over 2 or by pi, and you change things here. You change sines if you go to pi. Yes, and you change cosine. No, you change cosine with sines.
Yeah.
And
Makes sense.
so that's the thing. Right. So the point here is to get to this that I write here. This is to use later several times because this is how to rewrite the A3 and the B mu in terms of the photon and the boson. So in fact, this is the A3 and B mu are linear combinations of both the photon and the Z boson. And the same with the AU, A1 and A2, they are linear combinations of the W plus and the W minus, as we have seen above. Above we defined what is W mu plus minus. Here it's just inverting the system. I just inverted the system and then recast it in terms of W's, A's in terms of W's, pretty much. And these are the physical fields. So A's, Z's, so A, Z, W plus W minus, these are the physical fields. So our option from here onwards is to write our Lagrangian in terms of physical fields so that we can have a taste of the real interactions that are behind it. Let's do that. So let's look into gauge bosons of interaction. So be ready for an amount of indices, Lorentz indices now coming about. So first of all, let's recall in the case of a abelian symmetry. This was last Thursday we talked about that. When we have this V mu, we don't have self interaction, so we can forget about this field strength tensor here. But this one is the non-abelian part, and we should take this into account. So let's expand this. So first, cubic terms. Let's just capture the terms that are three gauge bosons in it. First, they are written in terms of the gauge eigenbasis. So what is not mass basis is the gauge eigenbasis. You can call that way. In the Fairness, we can call it flavor basis, but it's also correct to name it gauge eigenbasis. We expand these things and we replace this. Now we have A3, we have A2 and A1. Let's replace with this above here, and we get these two possibilities: A0 with W's and Z0 with W's. This means that W's they have electromagnetic interactions, so this is an electromagnetic interaction, and they also have weak interactions because they interact with Z. Of course, there are plus permutations of the indices. In the quartic ones that are more difficult is where I'm going to do this in a more detailed way, leaving open to exercise that I will write. So, you have a certain spoiler of what will be some of your exercises here, if you want to start thinking about it.
Sorry, but I was just wondering how will that EM interaction look like, because it doesn't seem like it conserves something, because it has conserves charge. So
it does conserve charge, so W plus, W minus.
yes, but then it will have the zero momentum photons, right? because you could always go to the center of mass reference frame of the two outgoing double bosons, which has zero momentum. But you can't have that. But you can't have that on a photon.
So I don't understand. So maybe what you are saying is very smart and right, but can you can you say that again slowly, please, so that I
To have conservation of charge when without
Yes.
a photon decaying into two double bosons or
yes,
two double bosons annihilating in a photon.
which is what's happening here.
Yes, that's possible. But one also needs to have a conservation of power momentum, right?
Yes.
So if we are on the
Mhm.
other side of the diagram, we could go to the zero momentum reference frame because they are massive particles, but we can't do that with a photon because photons are massless.
So
But they carry momentum. They have a momentum.
Yes,
Yes.
but not in the center of mass.
We say that the center of mass strain, the momentum is zero, so before and after
It shouldn't be allowed as an asymptotic phase, but you still have interactions, those make sense, because those are,
the interactions are there, but
But
the photon will
but
have
those
zero.
have to be offshore directions because then
yeah.
the photon will need to have an effective mass, right?
Well, I don't think the photon needs to have an effective mass here. I don't see the because momentum is conserved.
Yes, yes, but the thing is,
So it is zero.
you can go to a reference frame where the outgoing momentum is zero because, but you can't do that for the photon. You can't have because you only have one component and it's the
Yes.
energy. You will need to have a zero energy photon.
Mhm.
But
Well,
for the massive side of the diagram,
So
on that,
the photon, so you have energy, so it has energy and momentum. Let's say if you go to the center of mass reference frame, but there you are in the so
the thing is,
Let's say
where
where-
you really can because photons are always moving at c. So
Yeah, yeah,
you
of
can
course.
Go
That's-
to the reference center of mass reference frame where there is zero
Yes.
momentum.
yes, yes. But I don't see how. What I'm trying to understand is how does it violate charge?
They don't value charge.
Two double bosons going opposite ways.
Yes.
That's the total momentum is zero at equation. So the photon, the resulting photon, in order to
Yes.
our conservation of momentum, but
Should I
at
zero
zero momentum,
Well, you
which
see.
doesn't make much sense.
Let me see. So if the two W's come with the opposite momentum, so they
Total momentum zero.
let's say but the thing is, what happens is that you come with two W's, they can scatter, they
Yeah.
can collide, they can
Okay,
scatter,
okay.
and they exchange a photon between themselves.
Oh, okay.
That's how you should see.
This is a vertex, not.
It's a vertex. This is not an interaction.
Okay.
This is a vertex.
Oh,
I think
okay,
that's why we were talking about different things, because we were thinking about something. I was thinking about something completely different.
This is a
Yes,
vertex,
this
but
is a
to
vertex which sets up an interaction. This is an electromagnetic interaction.
So it could do this, then the photon will go.
Exactly. Precisely. So
Like
Right,
I was
okay.
asking on.
Exactly, right.
We have the same thing in the
Yes,
electromagnetic.
the photon that goes to photon that.
Yes.
I was thinking about the full interaction, but it's only a vertex.
Yes, because when we have
Yes.
two leptons interacting, the
exactly.
resultant photon could also have zero momentum, but then decays.
Yeah, okay.
Something like that. If the
Yeah.
photon is here.
But you also drew the thing we were talking about that was the vertex. because-
Yeah, I was thinking about the vertex. I was looking into the moment. I wanted to make the point that in each vertex, the momentum is conserved. In each vertex, the signs of
Yes,
But since
but here we have a mass.
Yes.
Massive photon. That's
Exactly.
an offshore photon. so-
Yeah, an offshore photon here. Yeah, exactly. It's virtual. So,
Okay.
yeah, so that's
So it all makes sense.
since we're on this subject, how can in the full reaction the photon in quantum theory have no momentum or something?
how can the photon have no momentum?
In the full reaction, for example.
I don't see how can
Compared to
photon,
mass, it's the offshore.
Exactly.
photon.
Okay.
but you cannot. typically I used to say that you cannot store photos in a bottle. So you cannot stop them, you cannot put them with zero moments. They always escape the bottle no matter what you do.
But these are not asymptotic photons, so they can acquire this off-shelf.
Yeah, off-shell, yeah. They can acquire off-shell masses, and they can, this is a bit more complicated, I'm going to say, but they can also acquire thermal masses in high temperature regimes. They acquire a thermal mass, which has to do again with energy principles and so on. So the ground state is no longer zero energy, but the ground state is a certain finite energy, and therefore the photons at, let's say, in the ground state have the energy that you are giving to the vacuum in that sense, which is a difference to the ground state at zero temperature, of course. So, but this is an interaction. That's why this should be seen as I said, this is an interaction. It's an interaction vertex, and being an interaction vertex, this describes an electromagnetic interaction. Anyway, this was an interesting discussion indeed. And the same for the Zs. So here it's the same. It's a vertex. So again, this diagram that I drew here, this can be a Z here or a photon, and outside we have Ws. Right, and you have also permutations of indices. In the triple ones, I didn't bother to care much about indices. It's actually the simpler scenario, but you can find that in Peskin code, the book that I pointed out in the previous lecture. But one of the things is that because this is an electromagnetic interaction, this coupling here, this is defined to be E. So this is, we define G sine theta Weinberg as our electric charge. E. And this is why I mentioned, so in your exercise also, take G equal to E over sine theta. There it was not yet obtained, but now here I'm obtaining these things one by one. And of course, now you can, with this definition, you can recast it, and your electromagnetic interaction is here in the first term. So we have E, and this is the electric charge. So that's why you have plus or minus electric charges, because the plus or minus is with respect to E. So then you use natural units, the same story that we might discussed with the Planck constant and the C in the very first lectures. The E can also be put to normalize to 1. You can write things in units of E. Here I'm going to use E's all the way, but the electric charge is signed in front of this E. On the other hand, the weak charge, let's say, the weak charge of this is cot theta, plus or minus cot theta. So these are the weak charges of the W bosons. So what is the intermediate conclusion that we have here? That the W bosons are sensitive, and you can look into these vertices here, are sensitive both to the electromagnetic and weak forces, with electric charge plus or minus E, and with weak charge plus or minus E cot theta. Also, the Z boson does not interact with the photon, therefore it's neutral. But I can also say that the photon does not interact at the triple vertex level with the Z boson, so it also does not is not sensitive to the weak charge, to the weak interaction. There are quartic vertices that involve these things, but quartic vertices are no longer an interaction vertex. Let's say. They are interactions. Let's put it this way. They are interactions. They derive from the fundamental symmetries, the fundamental interactions that we have. They are interaction vertices, but the triple vertices is where you see what are the charges of these particles. Let's say it's not in a quartic vertex that you get the charges.
Not like you get two Z bosons collapsing into two photons, right? That would violate.
No, that would violate. Yes, that exactly. That is not possible. Right. So let's then look to quartic terms. These are the fun ones to look for. So first, this is the Young-Mills Lagrangian that we have obtained before. Here, just to recast it in terms of so I changed a little bit indices here to be consistent with some notes that I had on my own, so that I could track the indices, because this is prone to where when you do this. And I took the liberty of doing this all this job again. Then you do, well, I took what I did on my own. It's for exercise. I am only putting the results here. So then you have these 4 factorial possibilities of permutations among the Lorentz indices. So 1 is already here, and then you have you have the remaining ones coming from here. And as I said, this is an exercise. It's possible to show that the 4 vector boson vertex yields this thing here. At the level of the generic Young-Mills theory, this is the Young-Mills Lagrangian for the 4 vector boson vertex. In this case, the 4 vector bosons were these A's. So you can write this. These F's are the structural constants. Here I'm using the Einstein summation convention here with up and down indices. As I said here, so these are joint indices, so there is no problem in putting them up and down, because there is no meaning associated to the fundamental or anti-fundamental or something like that. So we are free to do that. Now, let's focus on the case of the SU2 interactions here. The first thing to recall is this property. Yes, the structural constants of SU2. They are the epsilon, so the legacy beta tensor. So you know this sum. This is a well-known result. It's because of this minus is because of the anti-symmetry, and you can use it. So now let's use this from here onward, and again using this. So I'm putting again these things here, and also G. I'm also using G that we've obtained. One obtains the following vertices. Again, this is again going to be an exercise to derive this. This one is not very complicated. It's fun actually to play around with indices. And of course, you can have more permutations of indices here, but when you extract the interaction vertex, you pick up one of the mu rho sigma possibilities. And you have this. So a vertex with 4 double bosons that we were talking about. This is one of the things that comes out of expanding the Lagrangian. A vertex with 2 Zs and 2 double bosons. Again, this is an allowed interaction that comes directly from expanding our Lagrangian. And this is the Feynman rule. The Feynman rule is the prefactor times I, because it comes from the path integral formulation where you have an I in the exponential. So, and then you do the expansion to all orders. Each order in this expansion is an increasing number of loops. So you're starting with 3 lambda, which is what we're doing here, and then higher orders going to higher loops, so quantum effects, and that I comes about there. So that's why we always put in the Feynman rule plus I minus I. So the third interaction, 2 W's and 2 photons here, and finally, at last, and also bear in mind, so here you have this the indices, so the Feynman rules and the indices here. This should be, this way I confirm with the Recasting further, and I've got exactly the same result. So this is, unless Recasting did the same mistake as me, I guess this is correct. And at last you have this vertex with 2 W's and 1 Z and 1 photon. So as well, you never have 4 Z's, you never have 4 photons, you never have 2 Z's and 2 photons.
Yeah, but there's acid. You said it's in the cubic terms that we see the charge, but
yes,
we can see them as well. Right?
Yeah.
In this case, the electric charge.
Yes, yeah, it's conserved here, but in the other scenario, it would be like the weak charge that would not be conserved. You would be violating weak interaction. It's a lot easier to think in terms of electromagnetic interaction. We see the plus and minus defined here, and we immediately understand that things are correct. But there are the charges here, in this case, weak charge, and that's not as intuitive but should be considered. So the conclusion, also the second partial conclusion, is that a pair of charged bosons is always present. Charged double bosons is always present. Here a pair of charged bosons is double bosons by definition, is always present. And the SU2L algebra does not generate any neutral vertex with only photons or set photons. Let's say these are all neutral vertices, the vertices. It would make sense talking about a charged vertex, because a charged vertex is a vertex that is not a singlet. It's mean you do the tensor products that you learn, and the charged vertex would be a vertex that would be a 3 or a 4, or depending on symmetry, or a 6 or an 8 or something. And vertices are ones. They are Lagrangian terms, they are ones in a good theoretical perspective. That's an invariant. The one is an invariant of the symmetry. If you have a 3, it's not an invariant because it transforms under the symmetry. And the Lagrangian, you want the Lagrangian to be an invariant. So now let's revisit the gauge boson mass spectrum, but express it in terms of physical parameters. Now theta, E, theta, and V. This is what we are defining as physical parameters, things that we can measure. We can measure E, we can measure theta, the V we can also extract from other measurements like double measurement and Z boson measurement, for example. So, and this, for this I come to this proposition first, is that the one gauge coupling G prime can be recast in terms of the electric charge E and one angle as E over cos theta. This is simple to demonstrate, this is not fancy, so you relook at the covariant derivative. This is what was written above. And you can write this in terms of, again, of the ladder operators. But let's focus on this last, the green part, because this is where the G prime is. And we want to conclude something about this G prime. So now we expand this, this bit here, and we get, taking the physical, the description of the gauge eigenbasis gauge bosons in terms of the mass basis or physical gauge bosons, here follows the expression you have here. We can apply G equals to E sine theta, and we have these two terms coming about. Which now we just solve this. This is just algebra that is here explicitly shown, and you come to this conclusion that at the end you have this interaction or this term here in front of A, and this is the covariant derivative of the broken theory. Which corresponds to the electromagnetic generators. Because of that, you say that this is equal to Q. All of this is equal to Q times E, of course, EQ. So you can identify this in this way. And from here, you take that now you have this G prime plus theta. So I'm following the reasoning here. So I'm saying this is electromagnetic interaction. So this is going to be this, or written this way, because we derived this before, and we identified all these names. So I just solved this with respect to G prime, and I obtained that G prime is in fact consistent. So now it's no longer God-given, as I gave you in the lectures, not the lectures, but it's also on the lectures, but on the exercises. But here it's, I didn't do this before because I think it would be too much talking about the electric. We would get to the same results in principle, but here we are really talking about the electromagnetic interactions. So for completeness, the covariant derivative in the broken theory gives a preserved part, which is the electromagnetic one. If you were to write just, if I tell you, okay, we have electromagnetic theory, forget about weak interactions. So you would write the covariant derivative as du equal to du minus I E, in this case, Q A naught. And this is what you have here. So this is familiar to you from the abelian scenario. This is in fact the abelian part. But here we can also write the broken part in the covariant derivative, because this will give you the interactions with the other gauge bosons, with the massive gauge bosons. Right? So now for the mass term, so remember this again that we were discussing. Now the W bosons is the simpler one. Let's just replace G and V, G and only G with the corresponding value E over sine theta, and at the end you get this expression, which is 1/2 of the W boson mass. This will have some importance doing these things in this way for some discussions. For the cross terms, let's say for these terms here, for all these terms here, you just do the same expansion. You write the fields here. Once again, I've done all the algebra here, and we can just skip the algebra. So this is for you to learn. You can follow this at home, but at the end you get something like this. Like this, exactly. So because here is where the physics comes about. You have terms, bilinear terms on the photon, but they cancel out. It's plus, but here it's minus, here it's minus. So we are very happy. We don't have terms. We don't have photon mass written in this way. Now the yellow ones. The yellow ones will be problematic because this would be but it's not diagonal yet. But it is, because this one cancels with this one plus this one, right? So it's tangent theta, you get tangent theta, so here it's with minus sign, here it's you have 2 plus signs. The green ones, it's exactly the same story, but you cancel them out, you have the signs, and you are left only with diagonal terms on Z boson, as we expected. So here we are not doing, note the difference. Here we are not diagonalizing directly the mass matrix. Here we postulated, let's say this way, we postulated a rotation matrix, and we are applying that, saying, okay, this rotates to the mass basis, and what happens? And we are getting here the results. So you get all these bilinear terms on the Z, we just need to sum them up together. We get this cotangent theta plus tangent cot squared, tangent squared plus 2. And if this is not very evident, I just wrote this trigonometric identity here. This gives you 2 cosec squared 2 theta 1 there. So at last you get the photon mass, the W boson mass in terms of these physical parameters, and the Z boson mass in terms of these physical parameters. And this leads take us to an important result, which is a true-level relation, among W and Z boson masses. That basically the W plus or minus is equal to the Z boson mass cos theta. This will have important, it will allow us to discuss a few things, and this will have important consequences, as I will make concrete here. Let's do a slight abuse of rigor. We are not going to be extremely rigorous, but this will highlight, and I will explain why it's not rigorous, but this will highlight what I mean here. So, we take the W boson mass, the measured value, which is 80, let's see if you can see, this 80 jets, also the Z boson mass, 91 jets, and also the measured value of the sine theta. And now we use this expression here, and let's see if it matches. But we see that things don't match. In fact, here it's really far away from the measured measured mass. Not even with error bar. So this is an indication of the presence of quantum effects that should lift this mass to the actual body. So what is not rigorous here? In rigor, you have to put, because we have used a Z boson mass that is already corrected. So the measure takes account corrections. We have used a sine theta that already takes into account corrections. So this is not the most rigorous way because we are using things that are corrected to compute something that is not corrected. So you are having here some numerically it's hidden in numbers, but it's like having it's like doing a bad truncation in a power series. You are having higher order terms that are not being properly cancelled or compensated by
In
terms
this
of the
case,
same
there
order.
is really a huge difference.
Yes, typically it's if you do it in more rigor, but I didn't have elements here to do that, you get like 78 or something like that.
Okay.
It's still far away, but it's less far away.
It's not that bad.
But it's really an indication of the need for radiative corrections. This was on the
But
next
those
picture.
corrections can be predicted by the standard model at higher order.
Oh yes, the standard model. Here, there you go.
Ah, okay. But it's
You're-
not like that constant of correction, the ferromagnetic constant.
Yeah, it's like in the same way. It's not that, but it's in the same way. It's the same techniques to calculate that. So these are some
Yes,
possibilities.
but one isn't explained by the standard model, and this one is.
And this one is explained by the standard model.
Okay.
In fact, there is a parameter in standard called rho parameter, which is in fact the ratio. So the rho parameter is the ratio of the W against the Z boson mass, all squared. I'm talking about squared masses always. So the W over the Z, and then you use these formulas here. So the thing is, you take the measurement of the W and the Z, and you put it one over the other one, and then you take the measurement of this over this one, and you multiply. It should be 1. But that's a standard model prediction, because you are putting MW over MZ times MZ over MW. Essentially, is what we are doing. But you are taking different sources of measured quantities, and that standard model prediction is 1. What you get in reality is pretty much 1. It's a 1.00004, if I'm not wrong. And this is really a sharp cut on our freedom to choose new physics. This is something that I want to discuss during the next lecture, because that is a guiding principle for what type of extending Higgs sectors we can have. Because that quantity can also be written in terms of generators. And if it can be written in terms of generators, if you have a larger, so a triplet or a sextuplet or something else, that will have an impact on the generators and can modify that relation. But it's going to be easier to discuss with things in front of you that I don't have at the moment. It should be one of the last things. So let's make a break because just to say here something that we have all these possibilities. You are not. This is QFT. You're not going to do any of these calculations. Don't be afraid. This would be tremendous calculation, in fact. But you have here. It's the quartic vertex. You know that you build these diagrams with interactions that you have at the Lagrangian level. I guess that all of you acknowledge that this is a quartic vertex between 4 W's, between 2 W's and 2 Z's, and between 2 W's and 2 A's, or between 2 W's and a Z and an A. So here, when I write this, of course, I cannot put the W's with the A's here. It should be that, and it's only one. So, in fact, in rigor, I said the way I'm drawing here is that it's the same gauge boson going up and down, but you can have a vertex that has as a Z and and a W, sorry, and the A coming on the other side. But there is a problem that I'm thinking now, because here you would not, you could not convert them one into another. Yes, so that would you need some higher order correction, something here to bring them back to so that vertex would be allowed here, but then to convert them into another you could not do. So you should have a two-loop effect. So that's a higher order effect in that sense. You also have the triple vertices, and here you also agree you have two W's and the Z, or two W's and the photon on both sides. Here is with the Higgs. We did not, we're going to develop this one, I guess, below. But we have two W's and the Higgs. Here we have two W's and two Higgs here. And this one is also like, it's a charge current here that we will also see later today. This charge current, we'll see this for electrons. Okay, guys, let's make a break because you are tired. Let me see what's left to show for today to see if we can have a 15 minutes perhaps. I guess it's plausible. Yes. So let's make a break to
Drink something more.
yeah, exactly. So let's make a 15-minute break. So 5 minutes before 12, let's start coming back here. I will put the video. I will pause the recording. Resume recording. Okay. So let's move on. I think I underestimated a little bit what I could speak in this lecture. I think we are going to. Well, let's see. Maybe it takes longer than what I think. I will try to also to be slow. It's better being slow so that everyone can follow. So Mark, can you see? Right. Okay. Let me see. You guys online, can you listen to me if I'm here a little bit further away from the computer? This is fun. Let me do it once more.
That was a keyboard.
This is interesting. And this is being recorded on YouTube. This is going to be on YouTube. So you can think about this rotation matrix if it's with the positive or negative determinant.
It's positive.
Yes. Okay. So now we have closed the gauge boson self interactions and the key points. Guys, sorry. Before moving on, let me just say something about all this. I guess most of you know, or at least some. All these numbers, they were taken from. Let me see if you can see this. The particle data group book. This is the booklet, the small one. I also have the big one, which is in advance for everyone there in the office to use.
It's on the web.
This is on the web, but I like to have the things with me. Okay, maybe it's not that ecological, but also the numbers are not good.
As well.
Yeah, I prefer books. Typical. The small one, I always have two of these. One to be at home, another one to be with me. Sometimes I use it, sometimes I don't. It depends if you're doing numerical stuff or not. But this is very useful. Sometimes what is the down quark mass? I just forgot. You come here, you see. Right, okay, 4.67 MeV, and so on. I also have a big one, but it's an older one. The newer ones I bring to university for everyone to use. So the students and everyone else in the office. So Philippe, if he wants to use, and everyone else. The small ones I of course take with me, and sometimes I give older ones to students if they want or if they need. Typically, this is useful if you're doing numerical scans because you need to put physical parameters there. and you have all this information here. You have a lot more information that you will ever use here, in fact. But this is not only a table. You also have like big bang cosmology. It's what I just opened, like here and see.
Wow, awesome.
The Big Bang cosmology is described here. It's like a summary of some articles, key examples, exactly. Big Bang cosmology, neutrino.
I'm sorry.
Yes,
Oh, was that the PDG? Because I didn't hear what you said. I had a.
this is the PDG. Yes, exactly. I'm just talking about the PDG. It's not only a table, but it's also a book with which has some key equations and some key references for.
Yeah, it can be downloaded actually freely, so everyone can have them on their phone. So
Yes, you can actually, you guys, if you want, you can actually order it from CERN, and you can say I want this for scientific purposes and something.
For free?
Yes, this is for free. The library, the CERN library gives this for free.
I'm just gonna ask it on the phone.
Yes, you can ask either only this or this and the big one.
The big one's also for free.
It's also for free.
Yeah,
Yes.
no, the big one.
And the big one is nice because it's here it's like, for example, look guys, now you understand this. First, you guys online. Now you understand what this is, right? The quark model. You see that I will show you there. You see the tensor products here. Some yes online. Online.
I can't see it, but what page of the PDG is that? So I can see it.
So this is like you see like the tensor products there and so on. So this is that's why it was important to discuss all of that. This is just to show that this is only to see a 3 times 3 times 3 and so on. So that group theory part, there was a reason to do that in a sort of way. The practical part will be the calculation of the Sorry?
We're gonna be talking about quarks.
We will talk about quarks as well, but not the quark models. We don't have time to discuss the quark model. It's also nice, but I'm focused on the fundamental set. But anyway, yeah, you guys, you can order the PDG, both the small and the big one. I guess the big one you can also do that. At least I can. I don't think there was any restriction for someone else to order it.
It will look very good on the
Yes, it does look. I have two at the moment. One is but one is the previous one. And the thing is, there, here in the small book, you have like parts of articles, a summary of some key articles. In the big one, no, you have entire articles. You have the tables, and then the second part is like the entire article, but revision articles. It's not like a new concept or whatsoever. No, it's revision articles. You want to see what the electroweak, what is the status of the electroweak theory. You have there 2 Zealot models. You have there 2 cases, and what is the experimental status of another article with that. You want the cosmology. You want inflation models. You have that there in the PDG. Gravity. You have things on gravity there as well. It's a generic. It has many things that are related and important. Okay. Okay. Thank you. Right. So now let's after some noise here. This will sound nice in YouTube, I guess. After some chit chat, let's go back to physics. So we have looked at the 4 boson interactions, 4 vector boson interactions. Now we are going to look into what happens to the vector scalar interaction. In the standard model, this is to say interaction of vector bosons or gauge bosons with the Higgs, essentially. This is simpler because there are not as many indices as we have. Because the difficulty of the pure gauge sector is the Lorentz contractions. It's not a difficulty, but it's like so you need to pay a lot of attention because you have like four vertices, four bosons, you have four Lorentz indices, and you need to account for permutations and so on. You need to do proper count. I recommend you when you do this the exercise. I'm sorry, Mark, but you were coughing. When you want to get to these results here that I will ask you in exercise, that's why it's written here, exercise. If you want to start thinking about that. I just didn't give it yet because you are still solving the other one. Maybe João is up. I'm not solving the other one, but I will wait for that, and I will. So this I recommend, for example, to these permutations, you pick up Mathematica and ask for permutations. Let me make a spoiler, which is, I guess it's here. Okay, this is the solution. Right. So, and you have to. I start doing it by hand. Up until here, I start doing it by hand.
Even writing them out.
That was not a problem. Writing them out was not. Believe me, it was not. Yeah, I use Mathematica because I started here. I got to this point here, and I start not seeing more permutations. I said, okay, now I need to consider 3 permutations, and then I decide, no, I need to put this in Mathematica and get you just put permutations and then new row sigma, and it gives you no permutations, and then you just so this is kind of a spoiler, but it's but it's fun. It's quite fun to do.
Just 3 pages of symbol.
No, not good series.
No, I've had those.
But it's fun to do. But if you follow Mathematica, you will. Those of the tablets will be easier because you can copy and paste and erase. Which I think it's more than half of you at the moment. But of course, I should not count on this. You don't have Ilaria, right? I'm sorry.
What
But there is another, if you don't have, there is something. So Alexandra, she uses something that is Wix. Alexandra, you can use because with Wix,
Yes.
it's really easy. You can copy. Yeah, exactly. You write on Wix, exactly. So now I start writing by, I was using Wix, but now I start writing by hand again with this. Because it's even faster.
For example, when I solve the exercise, I try to do it in weeks. It's more organized.
Yeah, I really like your organization and solution. And most of you, I think. I'm not talking about those all.
Things on Mathematica into latex form, so you can just copy and paste.
Yeah, you can copy it as well. But not
Take form
I
and
just need to change some of the things.
Rob, you have to improve a little bit in the organization of your notes. But the content is typically there, of course.
I need an exercise.
You need to do that for your own good. So,
Yeah,
But-
again, been hearing it since
Because
fifth grade.
you know how to do things, you know do things well, but then you don't transmit them in the better way. So this is a constructive.
No.
I hope you don't mind. I'm saying this in front of everyone and in front of YouTube, so all the world will listen to this. But this is constructive, believe me.
Well, you said I know how to do.
Exactly. You do it. Okay. Yeah. No. I think you all know how to do things, and you are doing a great job. Right. So let's move on now to the vector Higgs interaction. So this is your electroweak part in the kinetic terms of the electroweak Lagrangian only in the Higgs sector. I think there is no need to explain again what is this. So this is like with our gauge freedom to fix to remove the bosons. So now we want to look to interaction terms. So this, in fact, this interaction is something that coming from this electrolytic Lagrangian, where I will look into interactions among all these guys that are here. And here, because I don't have that many indices to contact, in fact, I only have pairs of indices, so I can just apply the G nu, and I just put one index up, another index down, and I get this interaction. So starting with cubic one, so we have the Higgs couples. This is also going to be an exercise. The Higgs couples to using the same technique, the same procedure we used before. Write your Lagrangian in the mass base, expand and extract the vertices. So you see, you have the triple vertex of the Higgs with the Z bosons, and this is proportional to the Z boson mass. This vertex. This is already like, so the essence of your exercise is to show this, because when you expand, you will get the gauge couplings and the Weinberg angles and so on. But now, what I'm already saying here is let's express this in terms, the couplings in terms of masses, because this also tells us what are the dimensions of these couplings. In fact, let me just, I think there is. This is not, this should be without the square, I guess. Because the mass dimension of this is only mass. Let me check that. I think it's only without square, only n and only n double. But let me check that very quickly, because I have it here, I guess.
There was a similar thing in the exercises that I found, and the mass was square too. So.
But it was over v principle.
Okay.
Right?
Yes, over v.
Let me just, because I have this vertex schedule in the paper. Sorry guys, give me just this moment. Just to correct this immediately, because this is clearly not correct. The dimensions there, I guess it's over v, but I want to check this. Of course, when you do the exercise, you will arrive to the right conclusions, but I don't want to have it. So this is exactly. So this is the cubic GBV. So this must be missing a v here. Yeah, I think there is a v missing here. I think there is a v missing here because the dimension of this vertex is one mass dimension. I think it's like this. But I will confirm, and you can even confirm with when you solve the exercises. I suppose it looks the way it's written now. Right. So now quartic vertices. Quartic vertices. So you have the two Higgs coupling with two Z's, two Higgs coupling with two W's. And here the V was not forgotten. So this is a dimensionless coupling, that is a quartic interaction. So this has to do with the dimensions of the Lagrangian. So we have four. So two vectors and two scalars, it's a dimension 4. So vectors and scalars have the same mass dimension. It's 1. So 1, 2, 3, 4. So this is already dimension. So this is a dimension 4 already. So here it should be dimensionless. That's why you have m squared over v squared. Whereas here in the above, so this is 1, 2, 3. Being 3, and this is 2 dimensions. That's why I'm saying this is wrong. And here it has the correct dimensions. Only by dimensional analysis, I'm assuming that this is the final, this is the result over. I don't know if it has some other factors here. I don't, at the moment I cannot solve that, but you guys will find the correct value, and I will also look myself. Right, so the Higgs sector is this. This is all about the Higgs sector. And note something important. There are no couplings of the Higgs boson, and this H is the Higgs boson. These are vertices that you can see experimentally. There are no couplings of the Higgs boson with photons. In fact, the Higgs boson does not have charge. It's neutral. It's a real scalar that is neutral. So it does not couple to the Higgs boson, but it has weak charge. So it does couple in triple vertices and quartic vertices. Well, to Z's, and to W's. But now I have a question for you, just for you to think a little bit. The discovery channel of the Higgs was Higgs into two photons.
Well, it was probably in interaction with two doubles and the doubles again.
You are getting closer. It's not exactly that, but it's more or less along those lines. João. Because we're saying something, I don't know if you want to say.
No.
Right.
X to Z, Z to W. It's mediated by the
That's also going the right way. It's mediated. So the thing is, we have one of the channels was something. We have a Higgs, and then at the end we have two photons.
A lot of stuff can happen in here.
Yeah.
Yes, that's why I'm already putting here. So what happens?
This
Exactly. That's it, João.
This asks for a triangle.
And it's a triangle here.
Also.
So this is a one loop. This is a radiative. I don't want this filling inside. Here it's the Higgs. I put 0. It's not that. It's a fermion. So here it's, for example, T.
Those are fermions.
We have not yet studied the interaction of Higgs with fermions. We will study in a few minutes. Only electrons, quark for quarks is going to be next lecture. But I don't know. This interaction we will talk about today. This interaction we'll talk about today. The Higgs with tops. This is one of the possibilities: top, bottom, up, down, or any quark.
There's even some famous thing with the Higgs mass and the top mass.
Yeah. That's because the Higgs couples, the stronger coupling is of the Higgs with the top, because the top is the heaviest. As you will see, the mass is proportional to the size of the interaction between the Higgs and the fermions, as you will see just below.
The mass is proportional to that, or the interaction is proportional to the mass?
Depends on the way you want to see it. This is actually, I will ask a question to all of you here, including ones online. I want one by one to tell me what is. I will start here in the room. If I ask, what would you like? What do you think is more natural? The electron mass being light, or the top mass being heavy? What is natural? What requires an explanation? Mark, what would you say?
I guess electron is natural.
For you, electron is natural. The top mass is what requires explanation. There is no correct. For you, it's the opposite, right?
Yeah, I would go with the top mass being natural because it exists.
There is no correct or wrong answer, but it's quite interesting. So, overall, you think it's the top is,
Just as the energy scale.
and usual for you, it's also.
I would think that the natural is something that electron is not.
For you, it's natural, the electron being light. It's interesting. I also see a different pattern here. And for the guys online, Alexander, for you, what is more natural? Is the electron being light or the top being heavy?
The electron, maybe?
Okay, the electron being light. So we have 3 electrons. Etevaldo, what do you think is more?
Yeah, I don't know.
You don't know? Okay. Sorry. Let's keep this way. Merave, what do you think?
Actually, I would think that the fact that they have different masses is unnatural, but
Yes. I think that was actually the best answer, even better than so. But the thing is, and I also give you my opinion, and I told you there is not a correct or wrong answer to this. But from my perspective, I would see the top quark as the natural one, because it carries the size of the electroweak symmetry, the electroweak symmetry breaking. The electroweak symmetry is about 100 GeV, so the VET actually is 246 GeV, and the top mass is 174 GeV, so it's of the same order. The electron mass is so half MeV, so it's four orders of magnitude below. So it's from my perspective, the question that I usually ask when I'm doing models and working with them is, and when I think about flavor physics, is why are the neutrinos so light? Why is the electron also very light? A lot lighter than the electric scale. This is the way I see it. Because I assume that the natural size of the Yukawa couplings is 1, which is the size of the Yukawa coupling of that's why the mass is Yukawa coupling times V. I'm already a little bit. This is something we are going to discuss here in the fermion sector, but let's already start with this discussion right now. I see, okay, the mass is the VEV times the Yukawa coupling, but I'm assuming a priori thing that the Yukawa coupling is of order 1 around it. So I would expect all fermions with the mass around the electric scale. Even neutrinos, it's a different story.
But the muons and the taus
are in between. Also, that's also another question. Why are they in between? So why are the Yukawa couplings so different? That's what Merate said. And I think it's a very smart answer, saying, well, why the hierarchy? Not what is the most natural. Why the hierarchy? Because you can also think the opposite. You can think that Yukawa couplings are small for some reason. Okay, it's a dimensionalized parameter. Maybe there is some fundamental reason for them to be all small. So why are some of them very close to 1? Of course, I could reply, because gauge couplings are close to 1. So I expect Yukawa couplings to have the same origin, being of the same size. That's the way I see things, but this is by no means a statement of the universal truth. This is just
generation starts to get strange.
yes, indeed. That's why there is a big area of physics called flavor physics. So that's fine. I see the talk more natural, but the actual question is what Merade said. Why the difference? Why do you have so big hierarchies? And this is attempted to solve in flavor physics. From symmetric points of view, new symmetries that forbid some couplings that are 0, and then you have quantum effects that generate those couplings radiatively, and that's why they are smaller. It's a whole new world there, but it's how I see things. But here the point was because of this coupling. So this is the one with a larger coupling here, because Osvaldo said, okay, but it's the mass that is proportional to the interaction, or the interaction proportional to the mass. It can go in both ways. So you have this. What you know is that this is the largest vertex. These ones are identical for all quarks of the up type at least, because the gauge bosons, and you'll see this now, don't distinguish generations. But here you have the Higgs distinguish between generations, even and flavors. And here, this diagram is one that maximizes the probability because of the size of this coupling here. So this can be produced sizably at the LHC, and this was the first channel, because this is a very clean channel. When you have photons, this is very clean in the detector. To start with, of course, because now it's like direct channels like Higgs to B bar. This is another channel, and this is a direct one. To TT bar is more complicated, because the tops decay before reaching the detector, so they leave like jets, and they are not as clean as other channels. And of course, if you put here muons, this is like by far the cleanest of the processes. Once again, these are interactions formed, you have two Higgs and so on. These are only interaction vertices. Okay, but I wanted to call your attention to this, that the Higgs does not interact directly with photons because it does not have electromagnetic charge, but it does interact with the other gauge photons. So let's analyze the Fermion sector now. So we have, once again, the quantum numbers, and I did something here conventional, which is the convention. Previously, you had bars here, and you had, where you had bars, you had a minus here, but a plus here, and a plus here. Because you have this also written with C, and with C here. That's because I introduced this representation from an SU5 perspective, where you should have left-handed things put together in the same representation. You cannot have in the same internal symmetry representation left and right-handed. So you need to conjugate it, the entire left-handed to find the right-handed and so on. But here, at this level, we can simply conjugate what was conjugated. So you remove the bars from here, you change the signs of these guys here, and you already saying this is the right-handed part of the up part, this is the right-handed part of the down, and this is the right-handed part of the electron. With I being a family index, family of generation. Because this is, we already started this discussion. All parts and electrons comes replicated in 3 families or 3 generations. Families of generations, it means the same here. So this index, Greek index here, it's Y1, 2, 3. So, and they have this, the replication is represented this way. So the lepton, we have the left-handed ones that are doublets of SU2 because they put together neutrinos and the corresponding lepton, the corresponding charge lepton, electron, muon, and tau. And the right-handed parts are singlets. Note that we don't have right-handed, in the standard model, we don't have right-handed neutrinos. If you would have right-handed neutrinos, you could write a doublet, a right-handed analog of this. But you don't in the standard model. That's something that maybe happens at higher energy scale. And now you call this the tau, the mu, the e, you call this flavor. You can also call flavor like within a certain, within the tau flavor, you also have 2 flavors, like the tau itself and the neutrino. You can regard these things as different flavors of the same thing. In fact, the weak isospin in this case is what distinguishes between these 2 flavors in a way. And the same thing in the quarks. You have the up and down, so up flavor, down flavor, charm flavor, strange flavor, top flavor, and bottom flavor. And the same for the right-handed ones. So they have the up flavor, so these are the same flavor. One is left at the right, down flavor, and so on. Also, sometimes if I tell you up type quarks or down type quarks, when I say this, up type, the word type, I'm talking about all of these that are here. And if I mention you down type, I'm mentioning about these ones. And of course, including this. And in the leptons, I could say the same thing. In fact, the charged leptons, including the right-handed parts, we can name them like down type leptons in the standard model. And the neutrinos are up type ones. So the left-handed neutrinos kind of behave as the up type quarks in terms of Lagrangian, let's say.
So I have
yes.
I talked to you last week about the book that I had about predicting symmetry. And
I didn't understand everything you said.
yeah,
So
so, no,
I
it's just a small aside. I talked to you last week about this book called Predicting Symmetry by Jacob Schweitenberg. And so they open by saying what we can't explain, and they make it sound like it's a little strange that we have 3 generations.
Mm-hmm.
And it's 3 for quarks, it's 3 for leptons, it's 3 for, so.
Either strange or tantalizing.
Right.
And in fact, in this booklet, maybe let me see if I found, there is a fit for neutrino in terms of the Z peak.
I already know that there are no unitary families, right?
Yeah, there is no there is up to date, there is no fundamental, I mean, there are proposals, I don't, only in the big book it is there. I will try to find
I
that.
suppose that's the question, is there a fundamental reason why it's 3?
That's the question. What is the fundamental reason why there are only three generations?
Yeah, but we expect that there are only three because it has to do with some decay rates and the number of, that's proportional to the number of families.
Right.
There are several indications, but these are two different things.
Right.
There are phenological indications. One is that we only see three chiral flavors in experience. The other thing is there is like the cosmological constraints on the number of neutrino active neutrino families, and the number is like 3 or 2.99, something like that. There is a fit to that. This is what I was looking for now. I will try to draw here. There is a because then I will erase. There is like a plot which is this is number of events, and this is the Z boson mass, and then you have this thing, and this is this is mass, and this is MZ. There is resonance, and then there is a fit. So this is like the three generation prediction, three families. There is another one for, let's say, 4 families, which is something like that. And there is another one for, let's say, for 2 families. 2 and 4. And then you have experimental data points. And the experimental data points fall sharply on the 3 generation one. So this is also big, but sharply. They also increment the error bars by 10 to see something, and you hardly see the error bars. And that's
weird.
Yeah, that's still weird. Why 3? So you have a lot of indications that you have 3 chiral generations, and in fact, you also have, if you postulate the existence of a 4th chiral generation, that may be heavier. Exactly, that's wrong. That's exactly. So I did a tail here that is not supposed to be here. I will not put the tail now. Exactly, John. That's the thing. And I think that's the that's our left experiment.
Yes.
So what now I got lost. What I was telling you about the generations. Yes. So we have a lot of the 4th family. If you have a 4th chiral family that also has this chiral distinguish. So the W's and Z bosons will distinguish between another spell. This is what we want to learn in this section. But the chiral is something that W's and Z bosons see differently, the right-handed and the left-handed. In particular, Z bosons see differently the right-handed and the left-handed parts. They have different charges, weak charges. Not the electromagnetic doesn't distinguish them, as we'll see, but the Z boson, the weak interaction, sees differently the left and right parts. And that's what defines a chiral fermion. When W and Z bosons distinguish the left and right part. When the left and W don't distinguish, if they interact equally, we call them vector-like fermions. But if we postulate the existence of a new chiral family, a fourth generation, even if it's much heavier, you say, okay, it's much heavier, so you don't see it, and so on, there are still effects on corrections to the masses of W's and Z, so electric precision observable, that I will restrict the possibility. It's not impossible, but I will restrict it. I work on this for quite some time in trying to find some fundamental reasons for the existence of 3 generations. And in the models that I've been working, we postulate, or we use this quartification model that I have mentioned you here. I think it's here. Was it here? Was it? No, it's already. Mhm. Yeah, exactly. This quantification, where, so SU3 is already here to start with. SU3L will be split into SU2L and U1s and then for the breakdown. SU3R contains SU2R as well as U1s because that must be completely broken down. And you have an SU3 family here. And here you already have family triplets. And under this construction, there is no space for a fourth generation at all. This is a fundamental concept. When you have only SU3s, you can even make gauge coupling unification of at least these three to make a full unification. That now the details don't matter. But you have this SU3F which is you no longer make three copies of things, but they are a multiplet of the of SU3F. So of course the representations of this group they come in indices of at least three of them. So in the model, the quantification model, they have indices of three of them at a time. Always one index of this, and then so left-handed quarks have these indices, SU3 color and SU3L. Right-handed quarks have indices of SU3 color and SU3R. And leptons have indices of SU3 left and SU3 right. And all of them have indices of SU3F. So they have three indices each. So they are charged under three of them at a time.
The symmetric origin.
It's a symmetric origin for the Y3 generations. And it's quite symmetric. On the SU3s, and one of the hints is we have three families. So SU3, we have the color QCD, which is SU3 color. We can get electric symmetry out of these ones there. So that's a reason to postulate this. It's nice. It's quite I quite like it as well. Otherwise, I would not work on that. I'm now, and this also has other consequences like the existence of lepton quarks, vector-like leptons, vector-like quarks, new gauge bosons, maybe a bit heavy in this model. But that's okay. I have a note here, which is so family or generation. Family generation or flavor are not the same thing. Yeah, exactly. So do not confuse family. Sometimes they coincide. If you are in a complete diagonal flavor basis, generation and flavor coincide. In standard model, in fact, they almost coincide. Almost in the quark sector, it's not the same. But typically, if you're talking about family or flavor, it's not exactly the same thing. Family is this. Flavor is these are different flavors. We have two flavors within the same family. But you can also say, okay, I have a flavor changing interaction that changes this to that. This is also a change of flavor. Typically, we don't say change of family, we say change of flavor.
So is there something like so one of the explanations for neutrino oscillations
Mm-hmm.
that would be the existence of a sterile neutrino?
Yes.
That would be, will there be three of them as well?
Yes, exactly. But that's also a requirement because without the three neutrinos of that sort, and sterile neutrino is only when you're talking about the sterile neutrino, we are talking about a mass eigenstate that results from the presence of right-handed neutrinos in the gauge basis and left-handed neutrinos, and then things mix in some ways, and you get three active chiral neutrinos, let's say, and the sterile one. Sterile because the interactions with the standard model are pretty much close, and that acts as dark matter. It's not light enough to be active as well as the other ones, interacts weakly or very weakly. So the being sterile means or also that it's a dark matter candidate. In a way, there are constraints on sterile neutrino a lot, but this model that I mentioned to you of these 4SU3s also predicts that type of physics. A neutrino that we don't know if it's sterile enough, that's complicated. Picking up that the neutrino sector is 15 by 15 at least. It's not easy to, in that model of 15 neutrinos, 3 of them are chiral, the other ones are not active. But it's a bit hard to compute all of that. So we are working on that, but not yet there. But yes, that's something that you have in this type of models. Okay, mass generation for fragments. This is, we have already mentioned a lot about this in the last minutes. So let's start with the Lepton-Yukawa interactions. So if you say, I want to give masses to neutrinos, I want to, to leptons, I want to introduce a mass term there in the Lagrangian. So let me put a Dirac mass term, or in this case, written in terms of the Weyl projections, chiral projections. But you write this Lagrangian term, and then you look into the electric symmetry. This is a doublet, and this is a singlet. Clearly, 2 times 1 is 2. This tensor is 2, so it's not as Yukawa invariant. This transforms. There is an exponential with something here, and it's not. There is nothing to cancel out this exponential from the Lagrangian. Look at the charges now. Minus 1/2. So 1/2 minus 1, which is equal to minus 1/2. It's not 0. So this means that the exponential of the one part is also not cancelling out with 2 exponentials that of the transformation here, or the delta, the infinitesimal one, does not cancel out. So this is not one invariant. So this term badly breaks. So once again, here would be sort of crashing to death the gauge principle. It's not as bad as putting explicit masses on gauge bosons. That would be worse, but it's also bad and doing this. So let's do this in a gauge invariant way. So what do you see? One of the things you see is that if you put here somewhere a doublet, it's only left one doublet to making this an invariant, because you remember that the 2 times 2 equals to 1 plus 4. So you have the 1 there. That's what you want to single out. So it's only lacking a doublet somewhere here. If the doublet has an hypercharge that can compensate this minus 1/2, so if it has 1/2 hypercharge, it works. So you want this. This is what you need to make this an interaction like this invariant. Of course, this cannot no longer be a mass itself. It should be a dimensionless parameter, because fermions have dimensions 3/2. And you get this. This is a Yukawa interaction. You don't have mass terms for fermions, you have Yukawa terms like this. This is for leptons in general. And here, we can also say that in general, these indices, I and j, they don't have to be equal. They can be generic, or they can have a certain texture that is given by symmetry principles. If you are in the SC3 model, for example, of course, this would not be an interaction of that, because you would have 3s instead of the 2s and so on. But you would have a certain texture for the corresponding Yukawa matrix. Zeros in some places, and the field entries in other places. But this is the principle. A Yukawa interaction of this sort, where this is now invariant under SU2, and because of this, it's also invariant under U1. So this is an allowed term. And here, this can have 1, 1, 1, 2, 1, 3, 2, 3, 3, 3, and so on. But in the standard model, that's not what we are. So we are going to assume a flavour-diagonal basis in this treatment here, at least for now. Yeah, assuming a flavour-diagonal basis. That is, this is our Yukawa matrix. Let's make our life simple in this regard. And in the standard model, indeed, this is what nature is telling us, at least of diagonal ones, not they may exist, but not in the standard model itself. So, doing so, it simplifies our life. We only have to expand this, putting here the Higgs doublet. You have the right-handed part, and this term will give you the mass multiplied here, and this will give you the interaction with the Higgs. So different things. So here it's just an expansion. So I put the 3 generations here in an exhaustive way. You also have plus the emission conjugation here at the end. So I'm already putting the emission conjugate because they have the same pre-factor. I'm assuming that these y's are real. They don't have to be real in general, but here I'm assuming they have to be real. And when you do this, you can just pick up this yellow and green parts and write, now in terms of Dirac fermions, here, when I have left and right written, but if you see the bars here and gamma mu matrices and so on, it's chiral projections of Dirac fermions. Those Dirac fermions that have zero.
It's something in zero.
Exactly. A left-handed is something and zero, a right-handed is zero and something below. But the fermions that we see, so the electrons that we see are Dirac fermions, and then we should combine them into this type of interactions. This one of the homework exercises had this. So these are the lepton masses that we have in this simple formalism. And this is the Higgs electron interactions. So you see the Yukawa interactions. So the mass is proportional, as you see here. The mass is this. So the larger the mass, since V and square root 2 is the same, well, square root 2 is a number, V is the same number everywhere, so it's a free factor of this common. The only thing that distinguishes the masses is the size of this Yukawa properties. So, if you want to understand the flavor structure in the standard model, why three generations and why the hierarchies, because these are two different questions of all. Why three generations and why are they different? These are two different questions that may be related. Answering the three, it's easier to postulate this SU3s or other things. But answering why the hierarchy is that's the elephant in the room. And that's the $1 million, the Nobel Prize question. There are several proposals, of course, but you have to have experimental evidence of them in one way or another. And that's really the complicated part or the challenging part. Why are these hierarchies? Why I have to end up with something like that and with different numbers here? But not different, incredibly different numbers. And that's why, so the interaction with Higgs, now you understand that the interaction with Higgs is stronger for those that have a larger mass, because this is going to be the larger of the Yukawa couplings in the, at least in the left sector. It's the same, this is the same picture in the quartz that is left. So this is the chiral projection. This is just to show that indeed, now L it stands for any electron, E, mu, or tau. These mass terms, this is just to show that you can write them in terms of the left and right things, recalling that these two are zero. So you have seen this already a few times during the first module. So this is just to show that indeed from here, from this yellow part, you come down to this yellow part here. Just to, and when I say at home, for homework exercise that we should show details is something like that. It's like you say, okay, from here I get to here, but let me just show indeed that this is the case. It's a simple thing, but it's nice to have things systematized and explained. So when I wrote in your exercise, oh, you are lacking this or that detail, I'm talking about these sort of things. Okay, now for quark-Yukawa interactions. Now we have SU3s, so we have these tensor products with threes and also twos, because you have this is a doublet of SU2 and the anti-triplet, because I have a bar here, anti-triplet of SU3. So now you see that these Yukawa interactions, I'm putting them already because we understood that the mass term alone. So if you remove the phi's, this basically craps out everything. But with the phi's, you have, so the QCD part will be fine. This part will be fine with or without the Higgs, the three part. 3 bar times 3 is always 8 plus 1. So we always have the 1 there. But the 2 times 2 is only possible there when you have the Higgs doublets. And that is the same for the hypercharges. Look how the hypercharges neatly go together. But here I have a phi tilde. Typically we do this. to get this interaction working, you need to conjugate this phi. This is the sigma 2 Pauli matrix, and you can rename this in this way, but this is the 1, 2 minus 1 half. It's because if you have this one, this is the same field, it's just redefining, making this conjugation of charge. What happens is that if you have plus 1 half here, which is hypercharged, this term would not be possible. And this also has a significant impact because the verb will be here in this neutral part, no longer down.
Yeah.
And the point here is, look, to get down quark masses, so this times this is 0. So this already does not give you a term like ULDR. But then you have plus this times this part, which gives you interactions DLDR, which is what you want. In this way, because you conjugate it and change the place of the heats. So this is the phi tilde. Now UL times this with UR, and not the DL times this with 0 and UR. So from this expansion, you get, once again, without, this is just to say that we are again in the flavour-diagonal basis. Now I put the Dirac delta. So this index is summing with this, and this is summing with that, and this I here is not summing, it's just accompanying the value of I. Saying y1, y2, and y3. Or you can say it's still summing, you know, it's just getting the same value. And if you repeat the process, you get the masses of all quarks, down quarks, strange, bottom, and these are the down type quarks, up, sharp, and top. These are the up type quarks. Plus the interactions with the Higgs, starting with the down one, ending up with the top. This is the stronger of them because this YT is approximately 1. So this YT is approximately for the 1, more or less. 1 point something or 0 point something, depending on the energy scale we are talking about. Now, so was this clear? I think this is not a very hard thing. Now, for fermion gauge interactions. So we have the lepton kinetic terms. This is the same procedure again. So the kinetic terms of the leptons that you see here. L bar kappa L kappa. So the exact same lepton should be contracted here because you have this flavor should contract accordingly and generation as well. And this is for the LR, so I'm not specializing to one. Now I will leave this kappa as the family index that is contracting here. And the covariant derivative, now applied to L kappa, can be written in this way. So this is going to the definitions above that we have expanded. I'm just putting them here, putting back the y here, because now the y is not to 1/2, it's going to be actually minus 1/2. When applied to L kappa is minus 1/2. So I put back here, there we go, L kappa is minus 1/2. And when you replace this, you can write this matrix in this way. Already with the Weinberg angle, the electric charge here, and the W's, the Z's, and the A's, so that we can extract the interactions already. And the covariant derivative for DE, so the second one, you apply the same covariant derivative, but you need to change the quantum numbers here. For example, y is going to be 1, minus 1 here, and it's not a matrix because it does not have this part here. Sorry, this part is not there, and this part is not there. Everything that is SU2 is not there. ER is SU2 singlet. Recall that. Recall this. Let's go back here. ER is SU2 singlet. This, in terms of covariant derivative, is the same. There is no covariant derivative for SU2. There is only a term respecting to U1Y. So it's simple to write. You can go there and write it. What is it? Here. So it's only this. This is a matrix because this is in the isospin space, let's say, the internal symmetry space. This one, the internal symmetry space, is scalar, so it's a number, say. And there is only hypercharge. This is the only thing that you have there. So it's the standard covariant derivative that you learned in the first module. But of course, now with B mu should be written in terms of the photon and the Z. And now the physics emerges when you expand all of this. So this is to expand everything. You put everything together. So you have the doublet here. Already, this is already contracted with the doublet. And so this part here is this here. And this part here is this bit here. This is just, this term is, you can convince yourself by expanding it on your own. And you get to this. So let's see one by one and analyze one by one. So this is where the physics lies. The first part is just the kinetic terms, the derivative terms, the momentum dependent part. Then you have something here. So this is neutrinos, left-handed neutrinos interacting with the Z boson. So you need to look into the fields and read them. The second one is left-handed leptons interacting with the Z boson. And the third one is right-handed leptons interacting with the Z boson. So what is the first conclusion that we take here?
That the interaction, the coupling is equal.
Precisely. The coupling is different. Z boson distinguishes not only between the flavor, it doesn't distinguish family. It's the same for the first, second, or third family, but if it's a neutrino or if it's a lepton, it sees differently, even if they are both left. And if you're going only to like left charged leptons, it sees the left part with this Feynman rule, and the right-handed part with this. One is tangent minus cotangent, the other one is only tangent. And here there is also a one-off factor here. So this is the Z boson distinguishes the left and right chiralities. And this defines your chiral Fermi. When a Z and also W, as we'll see, distinguishes the left and right parts, you are in the presence of a chiral Fermi. When it doesn't distinguish, you are in the presence of a vector-like Fermi. Why? Why do we call vector? So let me go above a little bit and to make it clear for you. Should be here. This interaction that we are looking for. There is no left and right in the vector bosons, but it sees positive, negative charges. It sees all of them in the same way. So that's why we have a vector boson-like. It's not a vector boson, but it's a vector-like interaction. It does not distinguish between the components. Now, what about the double bosons? What you see here is it only sees the left-handed part, at least at your left. It only sees the left-handed part. It does not see the right-handed part. Once again, distinguish the chiralities in the sense that it does not see the right-handed one. So double bosons only interact with the left-handed chiral components at leading order. You can have like combinations of effective series where it can also have a coupling to right-handed, but it's not a leading coupling. Also, double bosons look at this because they are charged. They allow an interaction where you are changing a neutrino into a lepton or a lepton into a neutrino, depending on how do you see the interaction. So these are flavor changing interactions. Also, electromagnetic interactions, on the other hand, they see both chiralities identical. Or in other words, in contrast to weak interactions, they do not distinguish chiralities. So the electromagnetic are agnostic to that. So we can also use this EL. This is just to write in terms of an electromagnetic current, because you can write the L's, LR and LL in terms of. So you see, you have this. You have done this in an exercise. That's why I asked you to prove that the psi was Lorentz invariant and transformed as a scalar. And that's psi bar gamma mu psi. You also prove this is Lorentz invariant and transforms as a vector. And this is what you have here. It transforms as a vector. But you have the left and right parallelities here that you can compress in a standard electromagnetic current. That's why you can write J mu electromagnetic. This is your electromagnetic current density. This is just to show that the L and R go to zero. In fact, you expand and you see this is zero. But feel free to ask if you.
No, it's just the current. I thought the gamma disappeared.
Yeah, the gamma is here.
Yeah.
The gamma is inside this index is because of the gamma.
Yeah, exactly.
Yeah, and because this gamma or this mu here is contracted with the vector boson.
Yeah.
Go to the lectures of the symmetries, the Noether theorem, and you'll see this.
Yeah, I
There.
guess it's just from gamma zero to the zero component is going to be it's going to be just the side by side.
Yes, exactly. Right, now you can do the same for the weak charged and weak neutral currents, which you designate in this way, and obtain this, the Lagrangian, in fact, the kinetic part, it can be fully written in this way. You have the neutral, these are called neutral currents. That's why you need to be careful when you put new Higgs bosons. You can induce some flavor changing in these neutral currents. Those are the so-called FCMCs, flavor changing neutral currents, which are highly constrained but not forbidden. You have the charged currents, which in the quark sector they are responsible for something that is the CKM mixing, which we will also discuss in the next lecture, and the electromagnetic currents. This of course current densities that I'm talking about. The current itself is the integration in time and so on. So you can rewrite, so you have interaction vertices here. So these are the formulas, so this is just information. But we can also recast the weak currents, so we are not almost finishing. We can recast the weak currents in terms of the physical Dirac leptons. Again, so we should recall this anti-commutation relation between gamma 5 and gamma mu. And it's possible to show, now we pick up all these current densities. So the LL here, so this is a vector, transformed as a vector, as you said, but if you pick up the chiral projections, so this is so you put L here, and you take the left-handed projection, the chiral projection, which is what you have here, and the other one here. So I'm just writing the same thing, you see, so this is this, and this is this here. And then now you expand the bar one here that you have, and you get that doing this, but barring it, it's the same as every L bar PR, or PR on the other side, because you are commuting, you are doing this. So a gamma, the chiral projector is 1 over half 1 minus gamma 5, but when you do this, when you're passing over mu, you are putting a plus sign there. That's why it goes to the right-handed chiral projector. This is so L.
So what basis of we have in vector? The projector in calculus is 1, 0, 0, 0, for example.
Yes.
I don't see. I'm just taking that matrix and I'm doing the complex.
When you do the complex conjugate, when you do, you need to flip the order because AB.
Yeah, no, I can see the flipping the order.
Yes.
I don't see
The plus.
Yeah, I don't see PL going to PR.
Yeah, like look here. The first thing here, this is just what is written there. But then you have this. It's still not going, but you have a gamma 0 here, and then you have to flip this gamma 0 because exactly. And then this gamma 0 comes down to here to make bar again.
Yeah.
And then you have plus. So you have this, you have PR. But then you are going to flip with gamma mu. So a gamma 5 is going to flip with gamma mu again. And No, sorry, this is already the end of the story. No, no, it's not. It's not. It's going to flip again, which is what's happening here. It comes to PL squared. But PL squared is equal to PL.
Yeah.
So it's simply PL is here. So you can write this current, and when you analyze this in terms of Dirac fermions, you understand this is not a vector current. It's a vector minus axial vector current, V minus A, because the vector part is this, the gamma mu, and then you have the gamma mu gamma 5, which is an axial vector. If I didn't ask you, maybe next year I will, also to show that the psi bar gamma mu gamma 5 psi is Lorentz invariant, but transforms, so you have a flip of sign in transformation. That's a pseudo vector.
An axial vector.
Or an axial vector. That's why this is a V minus A current, vector minus axial current. And you can do the same for the right-handed part, but the right-handed part picks up a plus, and it's a vector plus axial current. And when you have a neutrino and electron, it's again V minus A. I'm scrolling quick because this is the same thing. And an electromagnetic current at last. You don't have gamma 5s in the game, so it's simply a vector current. This is realistically a vector current. So at last, you can write this, you have the electromagnetic current, but in terms of Dirac fermions, not its chiral projections, these are the currents. This is the structure of the current, and it's nice because you can immediately understand whether these currents are vector, whether they are axial vector or axial minus vector. With L equals to E mu tau and UL nu E mu tau. Okay, we are done for today. I hope you have understood this later steps. Yeah, Thursday it's going to be there. I think for you one here inside, so you know how to get there, right? Yes. CP3, the top floor. I already asked them. They acknowledged. Few 30 mark. Yes, and also online. See you all on Thursday, and I will stop recording now. Do you want?